Hello everyone, let's do another graph. So my next example is we want to construct a graph of the function 2x minus 4 over x plus 1. The first step is to compute the domain of that function. Here, the only way this function can crash is if the denominator x plus 1 is equal to 0, and that will happen if and only if x is equal to minus 1. So the domain of that function is every single real number except the number minus 1. So poof, that's my domain, r minus 1. It's always better to write the domain as a union of open intervals. So here we have minus infinity to minus 1 open, union minus 1 to infinity. So now we have 4 open endpoints. So this means that in step 2, we have 4 limits to define and, of course, to compute. So remember, the first thing you always do is you just set up the limits. So here we go. So I have 4 limits. The order does not matter. I'm starting with the infinities, and then I go around points, but it really doesn't matter. So here are the 4 limits that I'm going to compute. So I have the limit as x goes to minus infinity, and then the limit as x goes to infinity, then the limit as x approaches minus 1 to the left, and then the limit as x approaches minus 1 to the right. And then you compute them. So for infinity, so minus or plus infinity, because this is a rational function, I can just keep the denominating term. So if I just keep like here at the numerator, the one that dominates is 2x, at the denominator it's x, and I'm going to do the exact same thing for infinity. So I can really just use this shortcut where I'm going to keep the ones that dominates. So here, this is the same thing as poof, the limit of 2x over x. Actually, here you could use hospital rule because this is a limit of the form minus infinity over minus infinity. And because we're getting 2, this means that this corresponds to a horizontal asymptote at y equal 2. So we have an horizontal asymptote when x approaches minus infinity. So same sort of tricks for infinity. So I'm just going to make everything appear. So this is why I like to do infinity and minus infinity together. Normally, the algebraic tricks are very similar. So boom. Okay, so just keep the ones that dominate. So 2x over x. You could use hospital rule here. Simplify, you get 2. And this means that there's another horizontal asymptote at y equal 2. So always take the time to visually interpret these limits. Now, the limit as x approaches minus 1 minus. Of course, if you put minus 1 in there, you're going to get a division by 0. So we have kind of the green light to sub in minus 1 minus. And I like to remind you that when you are subbing in minus 1 minus, you just need to do it at the denominator. So at the numerator, to simplify things, I just put minus 1, but at the denominator, I put minus 1 minus. So the numerator simplifies to minus 6. And the denominator, minus 1 minus plus 1, you're going to get 0 minus, and minus 6 over 0 minus, that's going to blow up to infinity. And then if you do the exact same thing for the right side of that limit, so same algebra. So you can notice here, I wrote in red the reason why I'm putting minus 1 plus at the denominator. It's because if you put minus 1 in, you get a division by 0 that I wrote here. So the minus 6 over 0 in red is what's telling me that I am allowed to plug in at the denominator minus 1 plus. So when you are looking at what's going on in the denominator, sorry, I might have said numerator. So at the denominator, minus 1 plus 1, that's going to be 0 plus, and minus 6 over 0 plus, that's going to blow up to minus infinity. So on the right side, we get minus infinity, and on the left side, we get plus infinity. So those two limits tell me there's information here that I have now a vertical asymptote at x equal minus 1. So this is an example where we have horizontal and vertical asymptotes, and this is important to remember because these are the first things I'm going to draw to get the complete graph of the function. And again, it's really important to understand that in this class, the picture or the drawing the asymptotes are part of the graph. If the asymptotes are missing, the graph is considered incomplete. Okay, so that's it for domain. So very similar again. So really nothing new here. Step 1 and step 2, it's just like before. Now step 3 and step 4, this is what's new. So if you compute the first derivative here, so here we go, so boom, so I have to use the quotient rule. You can verify and simplify on your own that this is 6 over x plus 1 squared. I'm going to use this to fill up my supersign table, but to differentiate, I'm going to bring the x plus 1 squared up as x plus 1 to the minus 2. So I can just use a chain rule in order to compute the second derivative. So by using a chain rule, you get minus 2 times 6 times x plus 1 to the power minus 2 minus 1, which is minus 3, times the inside derivative, which is 1. But I will simplify this as minus 12 over x plus 1 to the power 3 in order to fill up my supersign table. So it's very important in step 3 when you're computing the first and the second derivative, you need to simplify it for 2 reasons. You have to find critical points with these formulas, and you have to use it to fill up the supersign table. So the simpler these formulas are going to be, the simpler the rest of the computations are going to be. So now for the critical points of f, I'm going to use f prime. So when I look at f prime, we see that it's undefined when x is minus 1, which is not a surprise here. The original function was not defined at minus 1, so it's this one. And if you are asking yourself, when is this function going to produce zeros? This is the same thing as asking, when is the numerator equal to 0? Well, the numerator is 6, so this is never going to happen. So here we go, poof. So there's really no new critical point with f by using f prime. And now if we study f prime prime, it's the exact same thing. The denominator crashes at minus 1, no surprise there. And the numerator, which is a constant, which is minus 12 here, is never going to be equal to 0. So here there's really one point that divides the supersign table, and it's coming from the original domain minus 1. So when you're building the sign table, this one is slightly simpler. The point of that question is really to have an example that introduces again horizontal and vertical asymptote. So there's only one interesting point here at minus 1. So the supersign table, again for the supersign table, 4 rows, one for x, one for the sign of f prime, one for the sign of f prime prime, and one for the visual representation of this sign table. So only one value here, interesting, minus 1, and everything is just, the reason why minus 1 is there is because f prime and f prime prime are both undefined, and we know why visually it's there. There's a vertical asymptote for that baby. Okay, so then we want to know what's going on before, from minus infinity to minus 1, and after, from minus 1 to infinity. So by using f prime here, like quickly, if you look at f prime, I have 6 over x plus 1 squared. 6 is positive, something that is squared is positive. So here, without thinking, I can really fill up this sign table and say it's positive everywhere. Meanwhile, if I look at the sign of f prime prime, so the numerator is minus 12, which is always negative. If I pick a number less than minus 1, let's say minus 2 plus 1 will be minus 1. If you cube it, it's going to be negative. Negative over negative, it's going to be positive. And then if you do the same thing with a value bigger than minus 1, for example, if we pick 0, 0 plus 1 is going to be 1. 1 cubed is going to be positive. Under the minus 12, it's going to be negative. And now the visual representation, again here, I have to do it in 2 shots because I'm not smart enough. So because of the sign of f prime being positive, I know my function is going to be increasing. So I like to write those dotted dots first. And then with the plus of the second derivative, I know that it's going to be increasing and concave up. So there's only one arrow that is increasing concave up, and it's that one. And then same thing for the interval from minus 1 to infinity. My function is still increasing because of the plus for f prime, but now the concavity is concave down because of the minus in the sign for f prime prime. So there's only one arrow that is increasing concave down, and this is the shape of my function. So we're almost ready now. We just want to have some information about some couple points to start with. Of course, minus 1 was important, but this reason why it's important because the function is undefined, so there's really nothing to use here. Because 0 is in the domain of the function, so we're going to compute the y-intercept. So if you plug 0 in the original function, you get 2 times 0 minus 4 over 0 plus 1. that simplifies to minus 4. And then if you replace x, so if you wonder what's the x value that will make this function equal to 0, well, the numerator is going to be 0 if the x value is 2. So at 2, my function is equal to 0. So now we're ready to plot some things. All right, now I have to draw my graph for the last step. So I already plotted the 2 points. At 0, the function is minus 4, and at 2, the function is equal to 0. So that's my y and my x-intercept. Now the first thing I'm going to do is draw the asymptote. So we know from step 2 that the limit as x goes to minus infinity is 2. So there's a horizontal asymptote at y equal 2. So I'm going to draw my horizontal asymptote, so with a bunch of dashed line, and I'm going to draw its equation, not draw, but write its equation, so at y equal 2. And then there's another one going to infinity. So at infinity, we also computed in step 2 that the limit as x goes to infinity, the function goes to 2. So there's another horizontal asymptote at y equal 2. And there's a vertical asymptote at x equal minus 1. So I'm going to draw that one also. So here we go. A bunch of dashed lines. Okay. So remember, this is part of the graph. I want to see the dashed lines, and I want to see the equation used for that line. So it's part of the graph. If the dashed line is missing or the equation is missing, it's going to be a graph considered incomplete. Okay, so I have my my asymptotes drawn, and now the only thing I have to do is draw the shape of the curve around these asymptotes and going through the points. So we know from minus infinity to minus 1, the function is increasing concave up, keeping the fact that I have some asymptotes to follow. So I'm starting around, so I need to be increasing, so I need to be above. So function is going to be increasing concave up, and as I'm approaching x equal to minus 1, my limit on the left side was plus infinity, so I have that vertical asymptote. So that's my branch here from minus infinity to minus 1, and then from minus 1 to infinity, I know that on the right side of the asymptote, my function starts at minus infinity. It's increasing concave down, so we just have to be careful here. So just do it the best as you can. So here we go. So that's an example of a curve that would be increasing concave down. If you need bigger points, okay, so to make it look more precise, that's fine too. So here we go. So that's the graph here of my function. So keeping in mind the asymptotes. And again, once the graph is done, always make sure that the domain is correct. So when I look at this graph visually, I can see that this graph has the same domain, as the one we've computed. I have outputs everywhere except at minus 1, where I have a vertical asymptote. What about the important limits? Well, if I write down the important limits, we found that the first important limit was the limit as x goes to minus infinity was 2. I see it here. It works. The limit as x goes to infinity is 2. I see it here. It works again. On the left side of minus 1, I got plus infinity. I see it here. And on the right side of minus 1, I got minus infinity. I see it also right here. So this graph is consistent with step 2. And then the shape, this function is increasing everywhere. It goes from concave up to concave down around minus 1. Minus 1 is an inflection point because it's not defined there. So everything works out. So always take the time to look at your graph. Make sure that it's consistent with your domain and the important limits. We've done this already a lot. Now the extra thing is the shape. Okay, so where it's increasing, decreasing, concave up, concave down. If there's any local min, local max, or inflection point, whatever you see on the graph must match step 5. All right, so for that graph and that example, that's it. That's all. Bye-bye.